Hello everyone. For this week's tutoring video, I'd like to discuss the mechanics of how the pendulum works, as well as how to derive the equation for the oscillation period of a pendulum. You may remember how in last week's tutorial, I discussed how ropes and similar devices have a force called tension. And this is important to know because the definition of a pendulum is a mass attached to a string or string-like object like a rope. Although you may hear the mass get called a bob when it's on a pendulum, but it means the same thing. Unlike traditional tension problems, a pendulum's tension will change as the mass bobs. So for example, in the middle point the tension will be different than at the endpoints of the period. And note that a pendulum only works if you have the mass straight down attached to the rope as the initial condition before you begin swinging the pendulum. Because the pendulum requires the mass to be in the air for it to work. And if you try to put the mass in the air in any position besides straight up and down, the force of gravity will make it go to its straight up and down position. And in fact, this is what causes the swinging in the pendulum as well. The tension in the rope can be approximated by saying it is the mass times gravity, or weight, of the mass attached to the pendulum. As gravity will always be working on the load, which in turn will transfer tension to the rope or string holding it. So it will look like this.
We've been to 3 targets now. He's like, well, I looked it up today because I was like, I'm gonna buy it online. Yeah.
Now that I have diagrammed the forces acting on a pendulum, I can show a derivation / mathematical proof of the oscillation equation. As you can tell, the pendulum is an example of rotational motion, as the mass and the string it is attached to will bob back and forth along an arc-like path. And so, the equations for rotational motion are slightly different than the equations for simple linear motion. With the equation for force looking like this, where torque equals moment of inertia times acceleration. Although it means the same thing as a traditional force equals mass times acceleration, just for rotating objects rather than straight linear moving objects. The symbol for rotational acceleration is the lowercase Greek alpha, and the Greek character tau is the symbol for torque. To more easily show how the bob moves along the arc. We can divide the force vector for weight into two separate vectors like we did for the inclined plane. And it would look something along this line. Where the angle refers to the absolute value of the angle relative to the initial position of the pendulum. L refers to the length of the string. And the two vectors that weight's broken up into is mass times gravity times cosine of angle and mass times gravity times sine of angle. Remember that cosine and sine are always perpendicular. As you can tell, the force of gravity causes the pendulum to try to move back to the initial position in the center, where the angle is 0. So the force of torque on a pendulum would look like this. Negative mass times gravity times sine of theta the negative referring to the fact that the vector is decreasing because the pendulum is moving back to the initial angle, times the length, which is the distance from the center, equals mass of the pendulum mass times length squared, again because it is the distance from the center of rotation, times angular acceleration. Now that we have visualized and shown logically what the formula for torque as it applies to pendulums is, we can move on to rearranging and simplifying this equation. The first step to notice is that you can cancel out the masses, and then you can manipulate the formula to get 0 on one of the sides by first dividing by L squared on both sides to isolate the angular acceleration. And then adding the left-hand side to angular acceleration to get 0 on the left-hand side. For very small rotations, i.e. where the pendulum only moves a very small amount from the initial position, we can assume that sine of angle is exactly equal to the angle. So the formula then becomes 0 equals angular acceleration plus gravity divided by length, angle. At this point, it looks like there's no way to simplify it further, but this is not true. Because if we take angle to mean the function of the angle over time, which works because the angle does change with time in a pendulum, then we can notice that angular acceleration means second derivative of the change of the angle, by definition of what acceleration means, and that for formulas with angles, the second derivative of cosine of angle is negative cosine of angle. And because we are adding two things to get 0, adding a positive and a negative would work very well for this formula. So in conclusion, we can say that the angle at a specific time is the initial angle times the cosine of angular velocity times time. This ends up being very useful in our proof because we know that the definition of acceleration is velocity over time, and that if you add acceleration and negative acceleration, you will get 0. Because of this, we can notice the first formula is saying the angular acceleration plus velocity times displacement equals 0. And notice that g over L is right where the velocity should be. So g over L is the velocity. If you know basic trigonometric formulas, you know that the period is equal to 2 pi divided by the angular velocity, where 2 pi assumes the angle is in radians, which is traditional for most trigonometry studies. And so, since we know the angular velocity of a pendulum specifically is gravity divided by length, the period should be 2 pi divided by gravity divided by length, which can be manipulated and simplified into 2 pi times length divided by gravity. Although the actual solution to the differential equation would be that is the square root of gravity divided by length for angular velocity, as angular acceleration is in meters squared, whereas angular velocity is in plane meters, so you would have to make a square root to get rid of the squared. However, I chose to ignore this detail up until this point for simplicity, and note that the assumption that the sine of angle is exactly equal to the angle only works for very small angular displacements. And so if the pendulum swings very wide, like for example at the extreme left and right endpoints, the equation will no longer be valid, and acceleration plus gravity divided by length times sine of angle equals 0 would be the simplest form. As solving the differential equation in this form is not very easy to do in traditional mathematics. And so instead would have to be approximated using a computer, calculator, or similar device. However, from experimentation and watching videos of pendulums, I believe you would only be 45 degrees off from the true position in time with this formula, with oscillations that wide. Now that I've shown you a step-by-step proof of how the pendulum formula works, and discussed the basic forces at work in a pendulum, I can discuss pulleys in next week's tutorial, as they are also a very simple machine that uses ropes, strings, and similar devices to work.